So yeah, if you want to follow me on Twitter, Denis AWS Rosa, and if you want to also tweet, use the hashtag Couchbase. It's good for me. So one thing about microservice is that no one really wants it. What I mean by that is microservices are distributed systems, and distributed systems are really complicated to develop, right? And when you think about monoliths, they are easy to refactor, they are consistent, they are easy to develop in general, but of course they can have high availability or high scalability, and of course with monoliths in general, over time you get a big ball of mud. That's why we had to start implementing distributed systems, and one of the best architectures that we have so far is of course microservice. So microservice is a necessary evil. But the problem is, I talk to a lot of developers, and most of them, I see that they start developing with microservice pretty much the same way that they develop with monoliths. And when you do that, you actually end up with something called microlith, right? Because it's nearly the same problems that you had before, but smaller and distributed. So over time, and then you see a lot of people complaining about microservice, and usually, yeah, this is because you're not with the right mindset. So in order to make your microservice architecture great, you still have to do some work and some planning. And this is what most of my talk is about. I would like to propose some architectures and some recommendations to how to improve your maintenance and let the microservice itself solve most of the issues for you. First of all, microservices, they do come as systems, but they have to be autonomous. No microservice is an island. They need to talk to each other, but you have to plan them to work autonomously. Pretty much like humans, right? We depend on each other to commute, but in general, during the most part of the day, we work autonomously. Cool. In order to make a microservice autonomous, I personally define that your microservice should have three main characteristics. It has to be easy to scale. It has to have some isolation from failure. It has to be, in some level, resilient and elastic. And when you are using microservices in general, it kind of is naturally easy to scale, right? Because now you have smaller services, and you can boost just the applications that demands more resource, or you usually have higher demand. But definitely that doesn't mean that your architecture had any isolation from failure, that your architecture is resilient, or or is elastic. So let's see how can we make our architecture isolated from failure. This is known as dependency hell. Basically, you have your microservice architecture, and nearly every service depends on each other. This is a common sign that you have some problems with your concepts of domain-driven design. So you have usually to rethink, because if you have two servers that depend too much on each other, probably they have to be the same. Okay, but now I have this architecture, how can I fix this, right? One thing to remove the dependencies is to cache data instead of asking for it. So you can, if you have a user and all your service usually depends of this user data, instead of asking directly, making a synchronous call to the user service to get the data back of the user, you can just subscribe to an event, and whenever the user data is updated, all those servers would need the user data will be notified, and then you store locally all the data you need. So whenever you need the data of the user again, you don't need to call the user. You can just query locally. This is one of the ways that you can cut some dependencies. As we are talking about dependencies, we also have to talk about communication. Yeah. In general, communication between servers, they can be implemented asynchronously. So just try to avoid as much as possible to call another microservice synchronously. And most of the problems is just a question of reframing the problem itself. For instance, let's say an e-commerce, like Amazon. When you buy something, you are just asking, you are just placing an intent. And then later, Amazon send you an email saying that, yeah, we got your order. And a few hours later, you receive notification that, yeah, I just executed your payment. And then one day after, they say, oh yeah, your package is out for delivery. So even if the payment service is out, you will be always able to place an order in AWS, in Amazon actually. So this is the importance of asynchronous communications in general. Of course, there are many other ways that you can add isolation you can add some isolation from failure, but this is usually the most typical ones. And yeah, now you can say that you have at least some good level of isolation for failure. But our microservice is not resilient yet. How can we make this resilient? First of all, let's update the last version of the protocol, right? HTTP 2.0 has been out there for quite a while, and most of the frameworks already support it. So let's do just a small test. So here is you can see the HTTP demo.io, and you can see how fast 500 images of HTTP.0 load, and then we can run HTTP.2, and you have a significant less time, the same content. And this by itself already can boost a lot your architecture, your microservice communication, just by changing the protocol itself. All right. Another thing is, in order to be resilient, you can't let anyone break your state. What I mean by that is, how many of you guys are familiar with the event sourcing and event logging pattern? Okay, good. So basically in event sourcing, every change that you receive, you store as an event, and you store in your event log. So even if something goes wrong, and let's say someone some other microservice sends the wrong data, you can always go back to your event log. Instead of update directly the database, you can go back to your event log, ignore this message, add a new one, and reprocess the whole message in the whole log, and everything will be consistent again. Of course, there is many challenges on this. It's not easy to implement sometimes. I explain in this blog post here some of the perks, but this is a very good pattern for protecting your microservice itself. I was working back then. I was working for a company in Munich which creates investment bots, and usually we receive daily. We received a lot of files from the custodian banks. And sometimes after 5 days, they would call us and say, "Hey, I sent you the wrong file 5 days ago. This is the right one." But we already have all this history of change, and then what? What we do? Like, can we roll back to the states that we was 1 week ago. And this is exactly what the pattern lets you do. And also it adds capability of temporal queries, right? Like how my object got in this state, or how was my state 1 month ago or 1 year ago. So it's quite cheap to implement because storage is cheap in general. It's just a matter of understanding itself the correct ways of implementing it. And of course, you don't need to implement in every single microservice. Just in the core ones are good enough in most of the times. Cool. So with this, you can protect yourself for, even if the other microservice has a bug, you can still easily recover from the consistency. Because one of the problems of microservices in general is once you have a bug, it tends to be distributed, right? Because then this microservice send the wrong data to the other one, and this other one has the wrong data and send the wrong data to another ones, and you have this distributed inconsistency. And this is one of the things that helps a lot to avoid that. Another thing that I would like to mention is to respect other service. For instance, let's say in service 2 is having a bad time, is for some reasons is dying, and then some user make a request to service 2 and and the thread is locked because it's waiting for the response. And then another user make a request to service 3 and it's fine, 200. Another user make a request to service 4, it's fine, and so on. But then over time, a lot of users make requests to service 2 and you have all the threads locked here in your thread pool in your main app. And congratulations, your whole service is down. And you think, like, how could this ever happen? It's quite a simple code, right? This is a plain Java. It's a very simple a URL connection that you are calling a service, and this already triggered this kind of error. And in order to avoid that, you have to just set both timeouts, the connection timeout and the read timeout, which is how long you are gonna wait until the other data start to stream, the other service start to streaming data. Okay, let's talk about secret breakers also, right? So the natural thing is, now I have my timeouts, and then the user make a request service 2 and 200, and then you make another request and you have a timeout, and another request 200, and then another request and a timeout. But over time, what happens is all your timeouts start to accumulate, and then again, your thread pool is full and you can serve any other requests. And again, your service is down again. So what I have to do is, let's implement secret breakers, right? So if you send a request and you basically the main concept in secret breakers is that after a threshold, you just cut the communication and all the following requests, they will fail automatically. And then in this way, you save your thread pool and other services can keep working. There are many other things that you should consider, especially when you are making asynchronous calls, like auto retries, authentication, bookheads, observability, and usually the main fix for that is to use Netflix histories, right? But what's the problem here? Like, we have a microservice, and then you have to code all this behavior and make your microservice, protect your microservice of all those possibilities. And the side effect of this is you're pushing too much responsibility again to your microservice, right? Because you have to think about all the scenarios. In order to address it, one of the common patterns that we have been using is exactly the service mesh. This is what our previous talk also mentioned today. And the service mesh is just a proxy. So it is the proxies that already handle most of these problems. Like if you have a bad gateway, for instance, the proxy itself will try again automatically. Or if you fail, if you have too many timeouts, the service mesh will will break the circuit. And of course, from the point of, from your service, you are just making local requests, and the service mesh is responsible to route the communication to the right service. And this is just, you just get free, you're just getting rid of all this complexity of managing the network itself. And it also has a huge advantage because it will basically work the same in production and in your local machine, right? Because what changes here is just to who service mesh is redirecting messages. And in general, if you are using Kubernetes, this is usually runs as a daemon, or we call it as a sidecar also. So in every pod, you have this service mesh to get in this running in the same pod as your microservice. As mentioned before, some of the most popular service mesh providers are Linkerd. It actually was the very first one. Envoy and Istio. I'm not going to spend too much time on this because the previous speaker already did a very great job explaining this. And we also have, and this is the Linkerd panel, so you can see some stats and literally the same thing that we saw before. Great. So now our microservices scale easily, is isolated from failure, is resilient, is elastic. Not elastic yet, actually. Let's see how can we make it elastic now. First of all, one of the easiest ways to make everything elastic is to use serverless and fully managed databases, right? Now we have much more options than before. So we have Kubernetes, we have Google Functions, we have Azure Functions. Lambda have been out there for quite a while. And we also have fully managed database like Cosmos DB or DynamoDB, for instance. And you don't need to manage your database. It's all managed by Amazon or Azure. But of course, there is some clear limitations of using serverless, especially when we talk about the size of your serverless function. So we have to also implement ourselves our elasticity. We have to make our service elastic, right? And when we talk about elasticity, one of the first patterns usually is service discovery load balancing. So in order to be elastic, you should implement those patterns, right? The service registry is quite simple. Whenever you spin a new service, the service registry itself in the service registry, and whenever you need to call, whenever an external service needs to call the service, he will ask to the service registry first, and then the service registry will return the right IP to call. Turns out that this is not how we do the things anymore. You can still do this, but indirectly. If you're running Kubernetes, for instance, you can just use service. So the service automatically takes care of the service discovery, and most of the cloud providers already support load balancing. So yeah, just by a simple configuration, you can get all the service discovery for free, which brings, eliminates the need of using frameworks like Eureka, for instance. You just don't need to use this anymore. Outscaling. Now that we have the service, the load balancing and the service discovery, now we can talk about outscaling. Same thing with Kubernetes. We have replica sets, so you can define how many instances you want of your service. And with Pod Outscaler, you can define that whenever I have 80% of CPU, I want to. You can say to Kubernetes, please spin up a new image. And you can also add some custom stats based on your application. Okay, so now we can say that finally our application is elastic, resilient, has some isolation for failure, and scale easily, right? Now my microservice is high scalable. Well, what about your database? Yeah, because if you think about databases, they are actually the biggest bottleneck of most applications. If you could keep everything in memory, your application will be blazing fast. But unfortunately, we have to store data in disk. And now we have all this multiple instances of servers talking directly to one single database. So the natural option is, okay, let's scale our database. Let's cluster our database. Turns out that it's not that easy to scale databases, especially when we are talking about relational databases. Relational databases, they were designed to run in a single machine. And when we create a cluster of MySQL, for instance, we're just faking the behavior of a big machine, right? That's why you can just keep adding machines to a relational database, because at some point, we'll just spend more time talking to each other than improving your performance. In AWS, I think the last time that I saw, the limit, you can have up to 20 instances of MySQL. And that's it. Like, you can go above this. And most of clients using Couchbase, for instance, they have 45, 80 nodes in the same database. So cool. That's why we start talking about polyglot persistence, which means let's use a proper database for each use case. If you need transactions, relational databases have been using this for more than 30 years, and they are really good for that. If you need search, Elasticsearch, Solr, yeah, they have developed. This is the use case for them. If you need recommendations, probably you might use a graph database, right? Because there's some kind of recommendation that you can only easily implement using those graphs. And of course, document databases, they are really good if you have a lot of relationships. For instance, in your code, you have your user, your preference, the preference, so you have the user telephone numbers and all that stuff. And in every single call, you have to bring back the user. And of course, in order to bring back the user, you have to make a lot of joins and bring out this data, right? So why not store the data all together? And this is most what document databases are about. Pretty much like other, let's say you have an e-commerce, and your product have characteristics, has descriptions, photos, and all this stuff. And again, you treat in your code as a whole, but when you store in the database, you have to slice different tables and rows. So this is what document databases are really good at. Just to give you an example, how many of you guys have seen this video before? So this is, yeah, you guys, I owe you a free beer next time. So these guys are basically some folks playing Pokemon Go on Central Park. And suddenly a Vaporeon appeared. And you see this huge flow of people going to the same place trying to catch a Pokemon. Pokemon, they started using a relational database, and they did some testing, and they realized that, yeah, this is not gonna work. And they re-implemented the whole thing using a document database, in the case, of course, Couchbase. But the thing is not talking about Couchbase itself, but imagine the user data growth. They went from 0 to almost 300 million users in a month and a half, right? And you can imagine how much money they made actually in this very first like 6 months just by being able to scale up and down. The last time that I saw, they made 1 billion in revenue in the very first year for a mobile game. And again, not everyone is Pokemon Go. but it's not about being Pokemon Go or not, but about using the right storage for each use case. Again, Couchbase in general is said in other documents database. They are the closest you can get from a relational database. Couchbase itself is famous for being highly scalable, not because we are better programmers, but because of some design concepts that we have in our architecture. We are memory first because we also have managed cache under the hood. And currently, I would say that Couchbase is the fastest database out there. Cool, but we didn't scale, we didn't make our database elastic yet, right? So that's why we have to talk about Kubernetes, databases running on Kubernetes actually, and operators. How many of you guys are familiar with the concept of operators in Kubernetes? Cool. So in Kubernetes, you can implement some custom behaviors, and this is what we call controllers. When you have a set of controllers for a given purpose, we call this an operator. We have seen that, of course, we can scale up and down our applications because they are stateless, but databases are stateful. You can just spin up another instance of a database, right? There is some work to do there. You have to make this machine talk to the others to join the cluster. You have to rebalance data. And this is exactly what the operators do. You can implement an application on Kubernetes that will manage another. This is a quite popular pattern right now for databases. MySQL also launched the operator. We also have operator for Postgres. And when we talk about databases, this is the next big thing, because now most of the infrastructure related stuff you can rely on operators to manage for you. And then they can they monitor your cluster, your database cluster, and if you see something wrong, the program itself already acts and spin up on a machine or kill a machine. This is one capability that we didn't have before because we didn't have any control of the structure of the infrastructure itself. This is part of what I'm going to demo today. So this is an example of how you can deploy Couchbase on Kubernetes. So basically, it's a very simple file where you can specify the version, how much memory you want for each service, your schema, and of course I want 3 instances, right? And this is basically how you deploy your database in Kubernetes. And when you want to deploy your operator, is just you can just download this template, this YAML file, and execute, and that's it. This is exactly what I would like to show you guys today. And one of the and I would like to also queue a machine and see what happens and show what happens actually. So, can you guys see? Okay. So here I have 3 nodes running on AWS. Kube control, get nodes. And then we wait. All right. So we have 3 nodes here. And then in this folder, I already have all the YAML files. So this is exactly, the operator one is exactly the one that I showed you before. So this is the operator. And then I can create. Cool. Now we create the operator. There's no secret here. You guys will be execute the same thing, probably. So So let's wait until our pod is running. Okay, so now our operator is already deployed, right? Let's deploy our Couchbase instance then. So again, I would run, it's the same file that I showed you before. Get, and here I'm saying that I will create a schema called default and with 3 nodes in my database. So I have to do here is kubectl control, create, what's the name of the file again? Couchbase cluster. All right, now we wait. Oh no, shit, okay. Get pods. Yeah. Then now we wait. Though, so the first instance was already launched and it's already running. And then we wait for the second one. Okay. The second is being created. It's being created. And then we wait for the third. Cool. So all of them are running now. So if I go here to I will for the port here to access the control panel. So I can go here. And this is the web console of Couchbase. And I'm actually accessing from this port. Cool. So you see here that all servers are already talking to each other, right? But what happens if I want to scale up my database? What I have to do here? So I can just go. Okay, I can just go back here. I have another file that I already changed. So in this file, the only difference is that I'm asking for 5 nodes instead of 3, right? So I can say kubectl replace -f Couchbase cluster 5. And then we wait again. Of course, with pod.scaler, you can just automate this process. So you can configure this based on CPU usage in memory. So you can also scale up and down your database. Of course, most of the database, and Couchbase included, have a replication. So even if you lose a node, it's fine because it will trigger the rebalancing. And this is exactly what I'm going to show you guys next. So now we have all 5 nodes here running. What happens if I kill a node? So let's see if I still have this working. Here you see that all nodes are already talking to each other. Here they are waiting they are starting. Let's wait for a little bit. They will trigger. Usually the operator itself, as you add a new node, the operator itself will notice that, oh yeah, we add a new node, and now what? What do? we have to move some of the data that was in the other servers to this new node, right? And this is done automatically. And now we just queue this connection. And okay, let's queue this node here, CB example 00. So this is the worst scenario, right? We have pods run, yeah, operators only. Okay, this is the worst scenario. Let's say you just completely lose a machine. What's going to happen is the operator will notice that you have lost a machine. It will trigger, it will relaunch a new one, because this is part of the Kubernetes pattern, right? Like they monitor, and if something is different than what you have specified, they launch other machines or kill machines to be consistent with your configuration file. And then once the machine is launched, the operator will automatically rebalance your whole thing. So they will move data from the old servers to the new one. So let's queue one machine here. kubectl pod cb example 0002. Okay, so now we don't have the pod 002 anymore. Then we wait. Here, it automatically recognizes that the node is down. Oh, sorry. And it will trigger a new instance, or at least it should. Yeah, so now we have a new instance, and the service itself will trigger the rebalancing. At least it was supposed to do. Yeah, so this is automatically done by the operator. The operator knows how Couchbase works, so we implemented the operator, and it noticed that the new node was added, and it called the specific APIs to automatically trigger all the stuff internally. It's also valid for indexes. You can also, we are also going to support backups. So whenever you deploy your database in Kubernetes, we will automatically trigger backups and save all the backups in persistent storage. So this is the power of operators. And yeah, the developers in general, they always expected database to work out of the box, when in reality it's exactly opposite. You have to spend a lot of time managing it. And fortunately, this is our current state now. So we are we are walking a path that, yeah, you probably don't need to spend a lot of time managing your database. And this is what I would like to show you guys today. We are also going to support a lot of other stuff, and you probably can try other operators too, because they are all really cool. Well, questions? Go ahead.
Hey, Dennis. First of all, thanks for the presentation. Really good, really fancy. And I'd like to ask a few questions. The first one is, let's say you have a cluster, right? And you have a few nodes, physical nodes, virtual nodes. When you deploy your cluster, the Couchbase cluster, does it take into account the
Yeah. The question is if we are aware of we are hack aware, for instance. And yes, this is a common, not just Couchbase. I think most of the operators out there, they have this in mind, and they try to run each pod in a different node to actually avoid those type of problems, because they are quite common, right?